Okay, today we're going to look at polar form of complex numbers. Polar form. Okay, so we've done rectangular form. So rectangular form, that's when we define our numbers, our real part of Z, imaginary part of Z. So this is our Argand diagram. So rectangular form is when you define any number as how far you go along the reals and then how far you go up and down. So this makes sense. So we can go across 2 and up 1, 2, 3 if we want to. You get up to there. And that's our complex number up there. In rectangular form, we've got 2 plus 3i, that number there. So this is rectangular form here, where you go how much along the reals, how much along the imaginaries. It's like a game of battleships. How far left or right, how far up and down. Okay, but this is not the only way to define a complex number. There are other ways. And we could say, if we start with, I'm going to do one that I know I can do in a nice and easy way. This is my good friend in rectangular form, 1 plus root 3i. It's a very good one. Okay, but I don't have to define it as how far to the right and then how far up. I can say, well, how far is this from the origin? Yeah. So what's its magnitude? What distance do I have to travel to get there? Yeah. And at what angle do I travel? Because I can define any point by how far I am away from here and in which way to go. Yeah, that would still be enough to define where this number is on the plane. So let's try and work that out. How far, what's its magnitude? So I'll call this Z equals. So we need to know the magnitude of Z. The magnitude of Z is the square root of 1 squared plus root 3 squared, which is of course 2. 1 plus 3 is 4, square root is 2. So this is a distance of 2 from the origin, and at what angle? Well, that's the argument of Z. And that's going to be the inverse tan. We did this in the last video. Inverse tan of root 3 on 1. Root 3 on 1, we've got pi on 3. So pi on 3, 60 degrees around. Okay, so how do I write that in what we call polar form? Okay, so one way to think about it is, I'm going to rub this out for a minute. Come back to it. Okay, so our number Z was equal 1 plus root 3i. Now, if I want to write this 1 in terms of the magnitude and the angle, yeah, so the magnitude was 2, right? To get the angle, I can use cos of pi on 3, because cos of pi on 3 is a half, yeah? And this makes sense. I'll just draw the Argand diagram again over here. I'll go 1 across and 3 up, yeah? So if I'm trying to rewrite this 1 distance, and I've got the angle, and this is 2, yeah? This is pi on 3, yeah? Then this length is cos of that angle, yeah? Because it's the adjacent to the angle. Yeah, so that's where the cos comes from. So 2 cos pi on 3, that's the same as 1. Yeah, plus I, now this root 3, and we'll get the root 3, 2 sine, remember this is the opposite side. Yeah, so I want sine of the angle, pi on 3, and that'll give me this root 3. Okay, so there we've got it. We've got our number in terms of the magnitude, which is 2, and our angle, pi on 3. So what we can do with that is we can write it in a little bit of shorthand, yeah, because that's the easiest way to do it. We don't have to write it like this. You can take out the factor of 2. Take out a factor of 2, it leaves me with cos pi on 3 plus I sine of pi on 3. And instead of writing cos pi on 3 plus I sine of pi on 3 every time, I'm just going to take the first letter I and sine. So cos I and sine. So I'm going to call that cis theta, pi on 3. This is just shorthand, cis for cos plus I sine. So to get this in polar form, as long as I know the magnitude and the argument, I can write 2 cis of pi on 3. And this is the polar form of this number, which is in rectangular form. Now on your CAS calculator, it will write it a little differently. So when you type in, and if you say convert this to polar form, the answer is going to be 2e to the I of pi on 3. Now this is the same, it's the same thing. These two things are equal to each other. You may think, well, where did this e come from? You know, we were talking about cos and size, and suddenly you've just replaced it with an e. You know, we won't get into it now. It comes from the Maclaurin series, once you and basically Euler's formula. So e to the I theta equals cos plus I, cos theta plus I sine theta. Okay, you can equate those two using the Maclaurin series for cos and for sine and for e, and melding them all together and showing that they're the same. But we're not going to do that. It's an amazing thing to do. You should do it when you've got the time. Okay. But that's it. For VCAR purposes, we'll just write all our angles as cis theta, cos I sine. Okay, so that's how we convert. Now, why would we do that? What's the point in converting to polar form? The two main benefits are multiplication and division. Okay, so multiplying complex numbers that are in polar form is much easier than in rectangular form. So if I start with u, let's go with u equals 2 cis, what was it? Again, pi on 3, my favorite. And v equals, let's do 3 cis of pi on 4. Okay, so we'll start with fairly simple ones. So when we multiply these two numbers together, let's find uv. What happens there? So we want 2 cis of pi on 3 times 3 cis of pi on 4. Now this is amazing. You're gonna love this. So I just multiply the magnitudes together. 2 times 3, that's 6. Cis of the sum of the angles. This is just wonderful. Pi on 3 plus pi on 4, and that will give me the answer. So all I have to do is add these two fractions together. Now, I know adding fractions with different denominators can be tricky. So what are we going to put it over? We're going to make a common denominator of 12. This is going to be 4 pi on 12, 3 pi on 12. So I get a total of 7 pi on 12. And we've got it. That's it. That's all we have to do. No expanding brackets, no FOIL. Makes it really easy. So what do you think happens with division? If you were to have a guess. Let's do division. Division of these two complex numbers. Let's do u divided by v. That's 2 cis of pi on 3 divided by 3 cis of pi on 4. Let's have a look at what happens. So again, the magnitudes, 2 on 3. Cis of, you guessed it, just minus those angles away from each other. How great is that? Okay, so what do I get? 2/3 cis. This is 4 pi on 12. This is 3 pi on 12. Minus them away from each other. 4 minus 3 is 1. Oh, made a mistake. There we go. 12. All better. Okay. So polar form, sometimes it is worth converting your rectangular form to polar form in order to carry out multiplication and division, because it is much easier. Okay. Now, there's one specific case that we can look at. Demoivre's theorem. He was French. I am not. So I say it like an Australian, Demoivre. Okay, so here we go. Let's do Demoivre's theorem. So if you have complex number z equal to r, so I'm going to use r for the magnitude of the complex number. So r cis of some angle. Yeah. Then z to the n is the same as r to the n cis of n theta. This is an amazing rule because as soon as you get, numbers bigger than 2, integers bigger than 2 in for n, this makes it incredibly easy to do the the multiplication over and over again. So let's start with u equals 1 plus root 3i, and let's do u to the 5. All right, so I'll convert to polar. Already know it. Already worked it out, which is nice. 2 cis pi on 3. So therefore, u to the 5, what's that going to be? That's going to be 2 to the 5 cis of 5 times pi on 3. 2 to the 5, 32 cis 5 pi on 3. How good is that? That is so much easier. And then you could convert it back to rectangular if you needed to. Just expand it out. So you can expand that out. 32 cos of 5 pi on 3 plus I. Oh, I forgot the 32 in there. Let's put brackets around the whole thing. And then I can say I didn't make a mistake. 3 pi on 5 pi on 3. There we go. So let's work that out. So it's just 32 bracket cos of 5 pi on 3. That's in the 4th quadrant. So we've got half plus I sine of 5 pi on 3. So we've got minus times negative root 3 on 2 over there. Then just multiply. Well, that's enough really, isn't it? 30. Let's expand it. 62, and this is minus 16i root 3 if expanded out. So that saved a whole lot of expanding. If we were trying to do this in rectangular form, that would have been crazy. We've been there all day trying to do that. So that's very handy. Okay, that's it for polar form.